Evidently today is donut day, so I should say to you, happy donut day. Do I look like I need more donuts? That's, I guess,
Did
the
you bring
question.
us donuts?
What was that?
You didn't bring donuts for the class?
If I just think this one through, Cassandra, if I had, what would be the next step? I pass it through the TV screen to each of you?
Yes.
You didn't think that one quite as through as maybe you should have. In my opinion. Okay, I'm just getting this camera set up. Okay, guys, let's get right into it. That section, hopefully, goal is to get this finished today. It's called L'Hôpital's rule, or L'Hospital's rule. And he was a Belgian, I believe, and he came up with this rather interesting result. Suppose you have two functions, f of x and g of x, that are of what's called indeterminate form. That's some number a. Then the limit as x tends to a of f of x divided by g of x is the same thing as the limit as x tends to a of the derivative of f divided by the derivative of g. What this allows us to do is to find the derivative, to find the limit of a fraction by using the limit of its derivatives. Now notice that is not the quotient rule, that is the top guy derivative over the bottom. So what do we mean when we say indeterminate form? Because basically you've got a fraction here. What is indeterminate form? 0 over 0. So when you plug x equals 2, you get 0 on the top and 0 on the bottom. Can you imagine that would be quite difficult to calculate, right? 0 divided by 0. No, the answer isn't 1. Could be anything. It's indeterminate form. And the other version of indeterminate form is infinity over infinity. So if either of these two situations occur, you can use L'Hopital's rule to find the limit. Notice these two combinations are not indeterminate form. If the top guy is 0 and the bottom guy is infinity, do you know the answer to that is 0? In fact, it's more like heck 0. It's even more 0 than 0 typically is. Right? Like 5 over infinity gets you 0, right? 10 over infinity gets you 0. What do you think 0 over infinity is going to get? Really 0, right? Extra special zeros. And infinity over 0 is not considered indeterminate form either, because the limit to that situation would be infinity, or it might be does not exist. But it ain't that guy. But let's show you that that is actually a very cool little niche market. Suppose I wanted to find the limit as x tends to 1 of x to the power 100 take away 1 over x take away 1. So we're way back to what, week 1. We're going to find limits again, but we're now going to use L'Hopital's rule. Well, the first thing you do is you check to make sure that you can use L'Hopital. Would you agree that when x is 1, x to the power 100 minus 1 is 1 take away 1 is 0? You agree that's 0? And isn't x minus 1 also 0? So it's 0 over 0. It is indeterminate form. So far, so good. Now, according to L'Hopital, and so what you do is you put an equals and you write a little L at the top, and everybody knows that when you stick a little L at the top, that you've just used L'Hopital's rule. And it's now going to be the limit as x tends to 1. Now, if you differentiate this guy, it's a power rule. And if you differentiate the bottom guy, it's 1. Now, plug in 1 here. You get 100 times 1 to the power of 99, which is just 1. You get the answer 100. So we have just found the limit of this fraction, and the answer was 100. That's pretty cool, right? Pretty smooth. Let's pretend you never knew L'Hopital. If I asked you to do that question in week 1, wouldn't the only technique that you could use would be factor and cancel? right? It's not a conjugate, right? There's not a square root, right? You can't evaluate it, right? You get 0 over 0, right? Can you imagine how difficult it is to factor x to the power 100 minus 1? The answer is, I don't even want to try, right? It would be ridiculously ugly, right? And I'm not even sure I'd have enough room in my paper to do it, right? So it's impractical. And so I'm glad that this guy L'Hopital came up and did this. Show you another one. Let's pick the limit as x tends to 7 of x squared take away 49 over x take away 7. Just doing a quick check. Yep, 0, 0. It's indeterminate form. If we use L'Hopital on it, you get 2x for the top one, you get 1 for the bottom, 2 times 7, and the limit is 14. Are we okay with that? I know I'm a bit quick, but it'd be cool. Differentiate the top, differentiate the bottom. 14 is the answer. I could check that one. If we used factor and cancel, which is pretty much the go-to method, the top guy factors, these cancel. Right? It works. I know which one I like to do. I like L'Hopital, now I know it. So if I had, if I had that question to do again, that would be the way I would do it. How about this fella? So the version question 7.
So what is the L'Hopital rule?
It's the fact that you can find the limit of this by turning it into that. So L'Hopital's rule says this thing can be done by finding this thing instead.
So you find the limit by using the derivatives to find the limit?
Yeah.
Okay.
So instead of finding the original question's answer, which is either very difficult or impossible to do, you change it into a different limit that has the same answer. And the different limit is the derivatives.
And it's only true for fractions, right? We just, anytime we
Yeah,
see a fraction.
this only works for fractions, f over g. Right. So I'm looking at question 7, trying to make sure I don't scan the wrong place. Oh, you don't need to write this. I'm just rewriting the question again because it looks ugly. First thing I'm doing is in my head checking cosine of pi upon 4, take away the sine of pi upon 4 is 0, root 2 over 2, take away root 2 over 2. Tangent of pi upon 4 is 1, 1 take away 1. It is indeterminate form. We'll now use L'Hopital to find what this limit is. Now, if you differentiate a cosine, you get a negative sign. If you differentiate a negative sign, you get a negative cosine, positive. What do you get if you differentiate a tan? What's the derivative of a tan? Come on, it should be
squared.
Yes. Now this guy, I'm going to evaluate at pi upon 4. So I'll take it over here. It's going to be negative the sine of pi upon 4. Take away negative the cosine of pi upon 4 divided by the secant of pi upon 4 squared. Okay, sine of pi upon 4 is root 2 over 2. Cosine of pi upon 4 is root 2 over 2. Does anybody know what the secant of pi upon 4 is? Okay, it's the same thing as 1 over the cosine of pi upon 4. So it's the same thing as the reciprocal of that, which makes it that. Which, if you make it look pretty, becomes that, which eventually becomes that. So all that hard work was just to find out the secant of pi upon 4. And so secant squared is 2. Now you combine these two guys together and you get negative root 2 over 2. And there is your answer to the limit. Think of that as a half, negative a half root 2, negative another half root 2. That's negative 1 root 2's divided by the 2 in the bottom. I guess the moral of that story is that you got to know some trig values, right? You got to know which secant of pi over 6 and pi over 4. Who knows, maybe next time cosecant. Since I'm kind of on trig right now, here's a version of another trig one. It's the limit as x tends to 0 of a tangent over a sine. Now, if you plug in 0, the tangent of 0 is 0, and the sine of 0 is 0, so it's indeterminate form. I can use L'Hopital's rule on it then. So this limit is the same as this new one I'm about to do. If you differentiate a sine of 6x, you get the cosine of 6x. Do you get anything else? If you differentiate the sine of 6x, you get the cosine of 6x. But what else do you get?
Times the differential of 6x. So it'd just be x, right? Or what? No, 6.
Yeah, it'd be a
Yeah.
6. Now, a tangent of 5x is a secant squared of 5x times a 5. Right, so they're both generals. Are you happy about where the 5 and where the 6 came from? Right. Now I'm going to plug in 0 and see what happens. 5 times the secant squared of 5 nothings is still nothing. And on the bottom, 6 times the cosine, well, 6 nothings is still nothing. Cosine of 0 is 1. Secant of 0, trust me, is 1. So it's 1 squared. The final answer, the limit is 5/6. And you can check it out. I'm pretty sure you know the cosine of 0 is 1. Well, isn't the secant just 1 over the cosine? So it's 1 over 1, so it's also 1. Very versatile, this technique, right? It does one job, but it does it really well. And its one job is to find the limit of a fraction, right? When the top and the bottom are indeterminate. So how about this fella? Okay, if you plug in 0, e to the 0 is 1. 1 take away 1 is nothing. Sine of nothing is nothing. It's indeterminate form. This becomes the limit as t tends to 0. Well, if I differentiate e to the 2t, I get e to the 2t times 2. If I differentiate a sine, I get a cosine. I should be able to plug in 0 now. 2e to the 0 on the top cosine of 0 on the bottom. There's our answer. If I had given you this question in week 1 and asked you what's the limit of this fraction, we couldn't do it algebraically. It wouldn't be the best we could do would be to do a guesstimate on a table of values. We'd pick a number like t equals 0.1 and then 0.01 and so on, and have a look and see if we could have a good guesstimate of what we thought it would be. We don't need to do any of that now. Isn't this quite a compact method? Try to sell it. I think it's, you don't really need to sell it, I don't think. I think it stands in its own merits. Well, let's show you that you can actually use L'Hopital for limits as x tends to infinity as well. This particular question. I'm going to do that one. Now, if you plug infinity in, would you agree x is infinite and e infinity is infinity? Isn't this an infinity over infinity version of indeterminate form, right? So I can do L'Hopital on it, and it becomes the limit as x tends to infinity. If you differentiate x, you get 1. If you differentiate this guy, you get e to the x. You can then plug infinity in. And 1 over infinity is 0. Suppose I did the limit as x tends to infinity of that guy. Okay, if you plug in infinity, you get infinity on the top divided by infinity on the bottom. It's indeterminate form. Let's do L'Hopital on it. Differentiate this guy, you get 6x take away 4. Differentiate the bottom guy, you get 4x. Now, if I plug infinity in here, don't I still get infinity on the top and infinity on the bottom? So you might think, well, I guess L'Hopital doesn't work all the time. You know, sometimes it fails. No. Isn't this indeterminate form? Can't I just use L'Hopital again? And the answer is yes. You can keep using L'Hopital until you get the answer. So I will do L'Hopital a second time. And if you differentiate this, you get 6. And you differentiate this, you get 4. Hey, we got an answer. Now, the old technique of doing this, remember when you would divide the top and bottom by x squared? Remember that technique? Wouldn't the answer still be 3/2? Do you see it works? Right. If you did it by divide top and bottom by x squared, can you imagine that would become, I cover this up. Can you see the answer is 3/2? You can almost see it's screaming at you, right? So I'm just saying, look, it does work, right? L'Hopital does get you the answer, right? I think it's pretty cool that it is able to do that. See if we can find. This is an 18 example. If you plug in 0, you get 1 plus 1 take away 2, yep, that's nothing. You plug in 0, yep, that's nothing. So I can use L'Hopital on it. That guy you differentiate, get e to the x. This guy, when you differentiate it, you get negative e to negative x. This guy, you get e to the x, and this guy, you get negative 1. So if I plug in x equals 0, I get 1 take away 1 on the top, which is 0, and 1 take away 1 on the bottom, which is 0. Oh, okay then. If it doesn't work, I'll just do it again. And the limit as x tends to 0. This guy gets you e to the x. This guy gets you a negative with the negative that's already there. So it's back to being positive. And this guy gets you e to the x. Now I'm going to plug in 0. E to the 0, e to the negative 0, e to the 0. E to the 0 is 1. What's e to the power of negative 0?
Also 1 because 0
Yeah.
can't be negative.
Yeah. Putting in negative 0 was probably not a good idea, but it is just 0. So you get 1 again. And so the answer is 2. A very versatile technique for doing a very specific job. It allows you to find the limit of fractions when that fraction is indeterminate form, right? When it's a 0 over 0 or an infinity over infinity. Really good at doing those jobs. So let me show you some things to be careful of. If you don't know the show, the context of this will not be familiar to you. But this is danger, Will Robinson. Danger. You get a really cool technique and you can fall for this trap. Here is the trap. Suppose I wanted to find the limit as x tends to 3 of x squared plus 5 over 2x plus 1. Now, away back in week 1, wasn't one of the techniques called evaluate? In other words, you just plug the number in, and if you get an answer, that's the limit. Now, if I use that technique, it's 3 squared plus 5, and it's 2 lots of 3, 6, add 1. That's 14 over 7, and the answer is 2. Be comfortable with that? It's 2. Now, if I take this, and it looks just like all the other questions we've been doing today, right? It's a fraction. And I use L'Hopital's rule on it. What do you think should happen? Do you think I should just get the answer 2 and I just did it a different way? Well, if you differentiate the top, you get 2x. If you differentiate the bottom, you get 2. And you get 2 lots of 3 divided by 2, and the answer is 3. It's worse than you just get the right answer. You know, you just did it in a longer way. Do you notice you got the wrong answer? Right? L'Hopital says the answer should be 3. The correct answer we know is 2. That's why I'm saying danger, Will Robinson, danger. Do not use L'Hopital's rule when you're not meant to. L'Hopital's rule should only be used when it's a 0 over 0 or infinity over infinity, right? Indeterminate form. That's why through every question I did today, do you notice I did the little check every single time? Because do you know the one question you don't check Isn't that the one sneaky one that they put in there to catch you? Right. So that's the first rule. Always check that your fraction is indeterminate form before you start using L'Hopital's rule, because you will get a number and you'll think it must be right because you did the methods right. No, if they're not 0 over 0 or infinity over infinity, L'Hopital's rule does not work.
What do you mean 0 over 0?
I mean that the top expression is 0 when you plug 3 in, and the bottom expression is 0 when you plug 3 in. Or in some cases, infinity and infinity. Right. Here is another, not so much danger, but here, this isn't wrong. This is just sort of what I'm looking for. Time consuming. Sometimes just because you can doesn't mean you should. You remember that rule? Just because you can doesn't mean you should. There are some questions that you can use L'Hopital's rule on, and they are correct to do it, right? It would work, but you probably shouldn't do it because the math is really ugly. One of those is almost always going to be one of these guys. What would be the typical method before I told you about L'Hopital for solving this question? And it's a method that involves a fraction and a word that starts with C.
Conjugate method?
Yes. You really should use the conjugate method on these questions. Now you might say, why should I? Well, typically differentiating with fractions doesn't end well. Let's show you one. An example of that would be question 16. Could I use L'Hopital on that question? The answer is yes, I could, right? It's 0 over 0. Do you know what happens when you differentiate fractions? Don't you get really, really ugly answers if there is square roots in them? I mean, what's the derivative of this guy? Well, you'd have to call it 1 plus 6x to the half. Then you differentiate it, and you'd get an answer that looks something like this, which then became this guy, which then became that guy. Can you see how ugly the math would be if you did L'Hopital on this? And look, there's another fraction over here, equally ugly. Could you use L'Hopital? Sure. It would work. If I was going to go really crazy, how about the limit as x tends to 0, not 0, 3 of Can you imagine differentiating those guys? Can you imagine how ugly the derivatives are going to be? You would be fighting through some really ugly algebra if you tried to use L'Hopital on that. So, moral of the story is, if you see a square root, it's probably better just use the conjugate method. It's going to save you a lot of grief. If you don't kind of follow that advice, well, you'll get the answer. You might not like how long it took you to get the answer, but that's a different question. So I'm scanning through, see if I can find some other weird ones. Oh, here's a weird one. Just came to note. Okay, if you plug in 0, 9 to the 0 is 1. Take away 5 to the 0, which is 1. 1 take away 1 is 0. 0 on the top, 0 on the bottom. Indeterminate form. It is not that long ago that we found out how to differentiate 9 to the power of t. Agreed? What's the derivative of 9 to the power of t?
The natural log of 9 times 9 to the t.
Right. And the other one is going to be the natural log of 5 times 5 to the t. Okay, now I'm going to plug in 0, see what we get. The natural log of 9 times 9 to the 0. Take away the natural log of 5 times 5 to the 0 over 1, so I won't bother doing that. 9 to the 0 is 1. 5 to the 0 is 1. And make it look pretty. There you go. If you were a guessing person, would you ever have thought that the limit of this weird fraction would have been the natural log of 9/5? I know I would never have guessed that, right? I could be guessing for here to the day I retire, and I probably still wouldn't get it. I guess there's probably a 9 and a 5 in the answer. I think that's reasonable to assume it's probably going to have a 9 and a 5 in it. But, you know, the natural log of 9 over 5, yeah, I don't see that being that obvious. Oh. Well, you put in L'Hopital, you get sine of 0, which is 0 over 0 in determinant form. And this gives me a new limit to calculate. It gives me the cosine of x over 1. And that's the cosine of 0 over 1, and that's 1. So the limit of sine x over x as x tends to 0 is 1. Let me try something out here. It's kind of interesting that this particular answer is 1, and that's because sine x over x is a rather weird looking function when you get close to 0. Right? So let's see if I can find the damn thing. Click on this. No. Give me a minute. Click on this. Good. Gotcha. Trying to find Desmos. If you're wondering what I'm doing here. Let's zoom over to Desmos and try that guy. Because there's another version of this I'm going to show you. It's even weirder. So I'll just put it in as a function. So y equals sine x. There we go. Yeah, sine x divided by x. And now I'm going to zoom right in. Now, do you see that guy is exactly where it should be? Technically, WebAssign doesn't do that. Shouldn't there be a hole there? Because you can't evaluate it at 0, right? Its limit is 1, but its value doesn't exist. Keeping that guy there, I want to show you this fella. Oops, my apologies. I'll write the damn thing again. I'll get this thing right in a second. You are going to look at that guy, and I hope you will say, but that's not really indeterminate form. There's a 1 on the bottom. But it's now a fraction. What's the sign of 1 over infinity? Well, it's the sign of 0. And the sign of 0 is 0. And what's 1 over infinity? It's also 0. Isn't this 0 over 0? Isn't this a fraction? And it's indeterminate form. Agreed? So I'm going to do L'Hopital on it. If you differentiate this guy, you get negative 1 over x squared. If you differentiate the sign of 1 over x, you get the cosine of 1 over x times the derivative of 1 over x, which is 1 over x squared. Now, do you see this guy here and this guy here are allowed to cancel each other out? So what you've now got is the limit as x tends to infinity of the cosine of 1 over x, which is the cosine of 1 over infinity, which is the cosine of 0, which is 1. So the function x sine of 1 over x, as x gets infinitely large, should flatten off at 1. This might break poor Webersine. And here we go. And I didn't break it. X sine 1 over x, I don't know why I put some extra brackets in, but I could probably get rid of them because it's the same function. There we go. There.
So reshare it. We can't see it.
I thought I did. I'll try again. You see it now?
No, I don't know why not.
It's like
I-
it's thinking about it and stuck.
So it's not that I broke Webersine. I
WebAssign
broke
doesn't
Zoom.
want WebAssign doesn't want to show it. You're right. It
Now we
wants-
can see it.
Can you see it now?
Yep.
Now, look at how weird this function is. Haven't we just proved that as x goes to infinity, that it levels off at 1? Can you see it leveling off at 1 here? I'll bring it back. If I shrink it there. Is that not interesting that that function has that value? Now, if you zoom in and do an x tends to 0, can you see the limit as x tends to 0 of that is actually 0? You mean it's zigzagging, but isn't it getting closer and closer to the origin? Very weird function. Before L'Hopital came up with his trick, if you want to call it a trick, or his rule, it was very difficult to find the limits of those types of questions. Very strange functions. So I think I've done all the good ones. I'm just scanning through, see if there's anything. Oh, well, I guess you might get caught out with this one. I hope you don't. This is version of 11. This is the limit. Oh, I do know something else I want to do before we're finished. We have this guy. Can you just trust me that it's 0 over 0, so L'Hopital is good? That guy there is 3x squared plus 5. And this guy here is just the cosine of x minus 1. And we still find the limit as x tends to 1. Only now we can plug in 1 and get the cosine of 0. And basically 3 plus 5. So the answer is 1. I don't think that was actually that big a deal. Okay, the last thing to look at is what is indeterminate form. So 0 on the top, 0 on the bottom is indeterminate form. Infinity on the top, infinity on the bottom is indeterminate form. And they're the only two indeterminate forms that we're interested in. But there are other calculations that are also called indeterminate form. I want you to think of that term as being, we don't know the answer. Not that the answer doesn't exist. That's different. You know, there are some limits that don't exist because on one side it's here and the other side it's there, right? They don't have a value because they don't have one, right? That's not the same thing as we don't know what it is. So here is a bunch of expressions, which I'm now going to zoom over.
Sharing again.
Yeah, that was me. It wasn't them this time. Here we go. Here is a whole bunch of questions or expressions. You see, some of them are ones, some are zeros, some are infinities. Would f times p, would f of x and p of x, would that be considered indeterminate? What do you get if you go 0 times infinity? That's essentially what we're asking.
0.
Why not infinity?
Because it's
I
a
don't know. That's
super
a good
zero.
question.
It is. So we don't really know, do we? So it's indeterminate form. 0 on the top, 0 on the bottom is, right? Infinity on the top, infinity on the bottom. That we use L'Hopital on those situations. But isn't 0 times infinity unknown? We don't know what it is. It depends on the situation, really. How about this combination? What would infinity take away infinity look like? That one can't just be. Infinity take away infinity. You're frightened to ask now in case you're wrong. God, number of times I'm wrong and the day's not even true. So come on, just be wrong.
0.
You're wrong. But it's okay, because it makes sense, doesn't it, that it probably could be. And that's because aren't we thinking of infinity as a fixed amount and that both of them are the same amount? But really infinity is vaguer than that. You know, you can't really nail it down. It's actually indeterminate form. Okay, analogy. There's an infinite number of whole numbers, right? 1, 2, 3, 4, 5. Would you agree that there's an infinite number of fractions? Right, a half, a quarter, 3/7. If I said to you, take all the whole numbers in the world and subtract all the fractions from the world, is the answer 0? Well, you might think, sure, they're both infinite. But think about it this way. How many fractions are there between just 0 and 1? Well, there's an infinite number of them. There's a half, a third, a quarter, a fifth, a sixth, a seventh, forever. And isn't there an infinite number between 1 and 2? So if I took all the whole numbers in one box and I had all the fractions in the universe in the other box, and I took the first one and subtracted the second one, wouldn't the second one be bigger, infinitely bigger than the first one, even although both of them are infinite? Do you see how infinity hurts your head sometimes? So if you don't know the answer, it's 0. Now, how about infinity plus infinity? And again, it's okay to get it wrong. Infinity plus infinity.
That's going to be infinity.
Yeah, that one, we know the answer to it. Right? You're adding something that's infinite and you're adding some more stuff to it. Isn't the answer infinite? Infinity plus 10 is still infinite. You know, that kind of thing. How about, I think that's it really. Yeah, I should add to subtract. How about infinity to the power of 0?
Is that one?
Nope, it's indeterminate form. Any number to the power of 0 is 1, Robin. Totally agree with you, right? 7 to the 0 is 1, 10 to the 0 is 1. Right? So that's probably where you're coming from. So let me try for the last one for today, argue why infinity to the power of 0, we don't know what it is. Okay. Right. 7 to the 0, 10 to the 0, anybody you like to the 0 is 1. So by that logic, quite sensible logic, infinity to the 0 should be 1. Okay. Seems logical. Infinity to the power of 1 is infinity. Infinity to the power of half, which is basically just the square root of infinity, is still infinity. Isn't infinity to the power of any fraction you like still infinite? So shouldn't infinity to the power of any number you like still be infinity? So if you approach it from that direction, is it infinity to the power of something? Infinity. Now, they do disagree a lot. So you might say, well, how do we find who the answer is?